Okay, we can start now a different topic, which is neutrino oscillations in the realistic case when we deal with three neutrino flavors and three neutrino mass eigenstates. Before discussing the case of three neutrino flavors and three neutrino mass eigenstates, let me very briefly discuss the general case of n neutrino flavors in order to get the idea of what we can expect in the three flavor case. If I have three n neutrino flavors, then the electronic mixing method should be a unitary n times n matrix, and the unitary n times n matrix contains n square real parameters. Out of these n square real parameters, n times n minus 1 over 2 are mixing angles, and the rest are the phases, the complex phases. Why is it so? Every mixing angle describes rotation in one plane, which is given by two axes. Therefore, the number of selections of 2 out of n is just binomial coefficient given this, which is n times n minus 1 over 2. And of course, the remaining are just the complex phases. Okay? Now, are all these complex phases physical or not? Can we observe them in experiment? The answer is no. It's easy to understand why. Well, if we consider the electronic mixing matrix, you remember it entered in the expression for the charge current interactions. And it was coming from diagonalization of the charge lepton and neutrino mass matrices. We can replace all the charge lepton fields by some phase factors, exponential I alpha I, for each left-handed charge lepton field. If we do that, we can change the phases of one line of the electronic mixing matrix. For example, we can make the first line of the electronic mixing matrix real by doing this. Or we can choose any other convention just to satisfy our needs. We can replace all these left-handed charge lepton fields. Now, we have to compensate this in order to keep our Lagrangian invariant. So we have mass terms, Dirac mass terms for charge leptons, and we can keep them invariant if we simultaneously replace the right-handed charge lepton fields exactly the same way. Then E bar left times E right will be invariant. Okay? And nothing happens. So we can remove n phases from this n plus 1 over 2 without changing any physical content of the theory. So these phases are unobservable, unphysical. How about neutrinos? If neutrinos are Dirac particles, we can do exactly the same, or almost exactly the same. We can remove some phases by rephasing the neutrino left-handed fields and compensate this by changing the right-handed neutrino fields. You remember that for Dirac neutrinos, we have both left-handed and right-handed neutrino fields. But we can only remove the phases from n minus 1 field, not n. Why is it so? Because by changing the phase of neutrino fields, we change the phases of one column of the electronic mixing matrix. And there is a term on the intersection of this line, the previously discussed line, and this column, which the phase of which is already fixed. We cannot modify it anymore. There is no freedom. And therefore, we cannot replace n fields of neutrino, left-handed neutrino, but only n minus 1. And altogether, there are 2n minus 1 unphysical phases which we can remove in this case. If we do this, we find that the number of the physical phase, the remaining number, is n times n plus 1 over 2 minus 2n minus 1, and this is given by this expression, n minus 1 times n minus 2 over 2. And from this formula, you immediately see that a physical phase exists only, or physical phases exist only in the case where there are more than 3 neutrino and charge lepton species. 3 or more. And the realistic case is 3. And in this case, there's only one physical phase which will be responsible for CP violation in the electronic sector, and which is called the Dirac type CP violating phase. Dirac type was because I was discussing now the Dirac neutrino case as an example, And one should remember that it does not mean that if neutrinos are Majorana, this phase is absent. Just the other way around. In the Majorana case, there will be some more phases. But this phase is there also in the Majorana neutrino case. Okay? It's just a term, the Dirac type CP violating phase. Now, if we consider the Majorana case, we should remember that the mass term in this case is not given by the expressions like nu left bar, nu right, but nu left transpose C, nu left. And in this case, there is no freedom to rephase neutrino fields at all. We can only rephase the charged lepton fields, but not neutrino fields, because these will always be non-invariant with respect to any rephasing. It's quadratic in the neutrino field and not of the type nu bar, nu. So no way to cancel. Therefore, there will be more physical phases. The n-1, which we could remove in the case of the Dirac neutrinos, cannot be removed in the Majorana neutrino case. They are physical. And for 3 neutrino species, which is a realistic case, we have 2 Majorana phases. These are 2 additional CP violating phases in the Majorana case, and as we shall see, they are in principle observable. They can lead to observable consequences. Okay, now, in general, we can represent the electronic mixing matrix as a matrix which contains only Dirac type phase, or phases, depending on the number of the flavors, times a diagonal matrix of phases which contains n-1 Majorana type phases. Okay. Shall these Majorana phases affect neutrino oscillations? The answer turns out to be no. If you remember, the evolution equation for neutrino oscillations in vacuum was given by Schrödinger-like equation, in which nu is a vector of neutrinos of different flavor. H is an effective Hamiltonian, and this is the equation which describes the evolution of the neutrino system. Okay? So if we remember that H can be written as U times diagonal matrix of the energies times U dagger, and here U, instead of U, we should use U twiddle, and then K is a diagonal matrix, and this is a diagonal matrix. Diagonal matrices commute with each other. Therefore, we can commute K from here to here and cancel it completely, and the result is independent on the Majorana phases. So unfortunately, we cannot probe Majorana type phases in neutrino oscillation experiments. And neutrino oscillation experiments can tell us nothing absolutely about whether neutrinos are Dirac or Majorana particles. And that's one of the reasons why we still do not know whether neutrinos are Dirac or Majorana. The oscillation probabilities can depend in general only on Dirac type neutrino phase. In the case of 3 neutrino flavors, only on 1 Dirac type CP violating phase. This turns out to be true also for neutrino oscillations in matter, as we shall see. Okay, so how many parameters do we have, and what are these parameters? We know that in the 3 flavor case, there are 3 mixing angles and 1 CP violating phase. What do we know from the experiment? The experiment tells us that for 3 neutrino flavors, for which we have 2 independent mass square differences, there is a hierarchy of these mass square differences. The one which is called delta m squared 2-1, which by convention is the smaller one, is measured in the solar neutrino experiments, and it was also measured with better accuracy in a long distance reactor neutrino experiment compound. The other one, delta m squared 3-1, was measured in the atmospheric neutrino experiments and in the accelerator neutrino experiments. And it turned out that there is a hierarchy between them. Delta m squared 2-1 is much smaller than delta m squared 3-1. More precisely, we have the following situation. Delta m squared 3-1 is of the order of 2.5 times 10 to minus 3 electron volts squared. And the mixing angle, which is responsible for the main channel of the atmospheric neutrino oscillations, which turns out to be nu to nu tau, is called theta 2-3, and it's very close to 45 degrees, which means maximum mixing. You remember, 0 or 90 degrees means no mixing at all, and maximum mixing corresponds exactly to 45 degrees. That was a surprise, big surprise, because until these experiments, people thought that probably neutrinos or leptons are similar to quarks. And we know that in quark sector, all the mixing angles are very, very small. So people thought that probably in the neutrino sector, in the leptonic sector, the mixing angles are also small. And it turned out that this is not true at all. And this was a very big surprise to many people. Next, from the solar experiments and Camlin, we know that the smaller mixing, smaller mass square difference is about a factor of 30 smaller than the big one, and it's approximately 7.5 times 10 to minus 5 electron volt squared. And the corresponding mixing angle, which is responsible for the oscillations of solar neutrinos, sometimes called the solar mixing angle and solar mass square difference, is about not 33, it's closer to 35 degrees. And the last mixing angle, until very recently we didn't know it at all. We only had an upper limit from the Shaw experiment, which was about 12 degrees. For many, many years, we didn't know whether it is even non-zero. And last year there was a breakthrough. Several experiments actually measured it. They found that it is non-zero at about 10 sigma level, and its value is very close to 9 degrees. So we finally now know all leptonic mixing angles, all three of them. However, we still know almost nothing about the value of the CP violating phase in the leptonic sector. This is much more difficult to measure. I'll discuss this. Okay, one useful parameterization of the leptonic mixing metric is the following. We know that flavor states, fields corresponding to the flavor states, neutrino fields, can be represented as linear superposition of the mass eigenstate fields with these coefficients, and index A corresponds to electron muon or tau, and index I to 1, 2, 3 to mass eigenstate. So the parameterization is UE1, UE2, UE3, and so on. Now from this formula and from its inverse, we immediately see that the lines of this matrix give us the composition of flavor state in terms of mass eigenstates. Okay. So the square modulus of this element gives us how much mu1 is present in the electron neutrino. This square modulus of this tells us how much mu2, the second mass eigenstate, is present in the electron neutrino, and so on and so forth. On the other hand, the columns of this matrix give us the composition of mass eigenstate in terms of the flavor states. So this element, for example, recently measured element UE3, which is just given by the sign of this last measured angle, theta 1, 3. This square modulus of this element tells us how much electron neutrino is present in the third neutrino mass eigenstate. This gives us the presence of the muon neutrino in the third mass eigenstate, and this gives us the weight of the tau neutrino in the third mass eigenstate. Now, I already discussed this master formula for neutrino oscillations, which is given in terms of the mass square differences and the leptonic mixing elements, the elements of this matrix which I am just now discussing. And there are similar parameterization, many possible parameterization of this matrix. We only know that it's parameterized by 3 mixing angles and 1 phase. However, we can define these mixing angles and the phase in many different ways. And one of the ways which turn out to be especially convenient, which is now called a standard parameterization, is the following one. We have a product, starting from right to left, of the rotation in the plane 1, 2, with a mixing angle theta 1, 2. This is cosine, sine, minus sine, cosine. Then rotation in the plane 1, 3, modified by the CP evaluating phase. And then finally rotation in the plane 2, 3 with a mixing angle theta 2, 3. And this modification can be expressed if we introduce the diagonal matrix of phases with elements 1, 1, exponential I delta Cp. Then this rotation, modified rotation, is given just by the product of these 3 factors.
The question.
Yeah.
up formula U with an asterisk. How does asterisk happen then?
Once again?
U, комплекс запряженная. Откуда это?
Okay. U is
Up.
Yeah.
Вот the.
Okay. The point is that the previous formula was for the fields, and this one is for the states. In order to obtain the state, you have to act on vacuum by the Hermitian conjugate of the field. And that's why the conjugation occurs. Okay, now if we do the multiplication, just plainly multiply all three factors, we get this result. This is, again, you can find it in the particle data group booklet, for example, what is called the standard parameterization for the electronic mixing matrix. It looks exactly the same as the standard parameterization for the CKM matrix. So the difference is only the meaning, what is mixed in this case. But the form is exactly the same. Now, we know from the experiment that there are 3 neutrino mass eigenstates and 2 mass square differences between them, which have some hierarchy. One of them is big, another is small. Therefore, we have essentially 2 possibilities for the hierarchy of mass squared here. Okay? One is that the state nu1 is the lightest one. Then there is a heavy state with small gap between them, and then the third heavy state with a much bigger gap between them. Another possibility is that these 2 states are upstairs, and the state nu3 is downstairs. Okay? Let me first describe the meaning of this color. So we have some bars here, which are shown, some elements of them are shown in different colors. If we take the area of each bar to be 1, then the weight of each flavor eigenstate is simply given by the square modulus of the corresponding element. For example, square modulus of this element, S13 squared, gives us the weight of the electron flavor in the third mass eigenstate. And from experiment, we know that this is 9 degrees sine of 9 degrees squared, which is about 2.5%. This means that the third mass eigenstate contains a very small fraction of electron neutrino. Therefore, the other 2 should contain the rest. There is a sum rule, there is unitarity. The sum of weights of electron neutrino in all 3 states should be 1. The same, the sum of weights of muon neutrino in all 3 states should be 1, and so on. And from experiment, we know from essentially atmospheric neutrino experiment that in the same third mass eigenstate, the weights of muon neutrino and tau neutrino are very close to each other, or maybe even equal to each other. And this is reflected in the fact that theta 2,3, the mixing angle which was measured in the atmospheric neutrino experiment, is very close to 45 degrees. Because these weights are given by squares of the moduli of these elements. And if theta 2,3 is 45 degrees, their square moduli are the same. Now, the composition of these 2 states, we know essentially from the solar neutrino experiments. We know that there is relative contributions which are of the same order of magnitude of electron, muon, and tau neutrino in the second mass eigenstate. And the contribution of the electron neutrino in the first mass eigenstate, the lightest one, is about a factor of 2 bigger than it is in the second mass eigenstate. And then by unitarity, we know that the contributions of mu and tau in each of these 2 are nearly the same. For each of them is nearly the same. What we still do not know whether these 2 closely related states are downstairs or upstairs. And this is called, this situation is called the normal mass hierarchy, and this is called the inverted mass hierarchy. But we do know that the state with the biggest contribution of electron neutrinos is lighter than the other one in this pair of closely related states. And this comes out from the solar neutrino experiments, and it is related to the MSW effect, to the matter-enhanced neutrino oscillations, which I will discuss later on today in my lecture. So remember this fact, that out of these 2 states, the lower one has a bigger electron component. So we know that how the ordering is organized between these 2, but we still do not know what is the ordering between these 2 and the third state. So whether the hierarchy of mass square squared masses is normal or inverted. In addition to this, we don't really know how far these states are from zero. We only know the upper limit on neutrino masses, which is of the order of 1 electron volt. But we don't know whether the lightest state and other states are all close to each other and close to 1 electron volt. Or maybe the lightest state is nearly massless, or has a mass something like 10 to minus 10 electron volt, which is for all practical purposes is zero. This we do not know. And the case in which all three neutrino masses are nearly equal to each other is called quasi-degenerate case. From the neutrino oscillation experiments, we only can measure mass square differences. You remember the formulas for the probabilities. They do not depend on the absolute masses of neutrinos, only on the mass square differences. So we should find other ways of measuring the absolute value of neutrino mass, or say, for example, the mass of the lightest neutrino. That would be enough. And I will discuss how people are trying to do this. Okay, now let us discuss what happens if we consider the properties of neutrino oscillation probabilities with respect to discrete symmetries, Cp and T. I don't discuss C conjugation because we know that weak interactions are maximally C violating. So C transformation doesn't tell us anything. But Cp is nearly symmetry of the standard charge current weak interactions. So Cp conjugation makes sense. So let me consider the oscillation probability in the form which is slightly different from what I discussed before. I will consider the evolution of neutrino state in time. You remember I told you that we normally deal with point-like neutrinos, so evolution in time and in space are equivalent. For me, it will be convenient now to consider the evolution in time. So I assume that neutrino of flavor A, which can be electron, muon, and tau neutrino, is born at the time t0, then it propagates and it's found at the time t as neutrino of flavor B, which may be the same or different from the initial flavor. Okay? And the probability of this is given by this expression. Now, instead of the distance, here I have the difference of the times, t minus t0. Otherwise, it's the same formula which I discussed before. And I want to study what happens with this formula if I perform Cp transformation or T transformation. Now, Cp transformation takes particles into their antiparticles. For example, electron neutrino, left-handed, under Cp transformation, goes into the right-handed electron neutrino. And the same for other neutrino species. So Cp transformation takes neutrinos to antineutrinos, which is at the formal level equivalent to saying that we should change the element AI into its complex conjugate. And since there is only one complex parameter in the expression for the mixing matrix, which is the Cp violating phase, this means that we should flip the sign of the Cp violating phase. And in the three flavor case, as we know, this is a physical parameter, the Cp violating phase. So the probability, if Cp violating phase is non-zero, the probability of neutrino oscillation changes when we go from neutrinos to antineutrinos. The probability of oscillation of electron neutrino into muon neutrino is not the same as the probability of oscillation of electron antineutrino into muon antineutrino. It's not the same. However, if there were only two flavors, it would be the same. There would be no possibility to have observable Cp violation. Only because we have three neutrino flavors, we expect that in general it's not the same. Unless this phase is zero by some miracle, or by some very deep reason, or equal to 108 degrees. In this case, it's also correspond to the real case. No complexity in the mixing matrix. Okay, now let us consider time reversal operation. Time reversal means that I should interchange the initial and final time of neutrino evolution. Now look at this formula. T and T0 enter into the exponent of this exponential factor. If I interchange T and T0, the exponent changes its sign, which is equivalent to the complex conjugation of this factor. But since I have a modulus here, instead of complex conjugating this factor, I can complex conjugate the other two, and the result will be the same. So if I complex conjugate the other two, it's again equivalent to changing the sign of delta Cp, the same as Cp violation. And also, you can see from here that if I complex conjugate each of them, it's equivalent to interchanging the indices A and B. So time reversal invariance is equivalent to interchanging the flavor of the initial neutrino state and the final neutrino state. If we started with electron neutrino and we are looking for muon neutrino, on the time reversal we should consider the situation in which we start with muon neutrino and consider oscillation into electron neutrino. And you see that formally the result is exactly equivalent to the situation which we had in the case of Cp conjugation. And this is not by chance. It turns out that Cp conjugation for neutrino oscillations is equivalent to time reversal. And this is just because our theory is CPT invariant. Any reasonable theory which is Lorentz invariant, local, and has the right connection between spin and statistics, and we have based our calculations on such a theory, any such theory should be CPT invariant. And therefore Cp conjugation should be invariant to, equivalent to time reversal, which is exactly the case as we have seen now. So, as I said already, neither Cp violation nor T violation is present in the case of n less than 3, for example, in the duplex case. And it's very easy to see that for survival probabilities, when A is equal to B, there is no effect of Cp or T reversal, Cp conjugation and T reversal. It's very easy to see because, for example, time reversal is equivalent to the interchanging the flavors of the initial and final state. But if they're the same, nothing happens. Okay. No effect of these discrete transformations on the survival probabilities. Now, how about CPT? On the CPT, we should interchange neutrino and anti-neutrino, and at the same time T and T0, which is equivalent to interchanging nu A and nu B. And therefore, on the CPT transformation, the probability of nu A oscillating into nu B will go into the probability of nu B bar oscillating into nu A bar. And it turns out that they are equal to each other, as they should, from CPT invariance. And you can immediately check it with this general formula, which we discussed already many times. And as I said, this is a consequence of CPT. Now, how could we in principle experimentally probe Cp violation or T violation? So, ideally, what we would like to have is to measure the probability of nu A oscillating into nu B and the probability of nu A bar oscillating into nu B bar and take the difference. If the difference is not zero, then we have some effect of Cp violation. Similarly, for T violation, we should take the probability of nu A going into nu B and subtract from it the probability of nu B going into nu A. And again, if it is non-zero, we have the effect of T violation. And as I already said, these two differences, the two asymmetries of probabilities, Cp violating asymmetry and T violating asymmetry, they are exactly equal to each other. And for the diagonal terms, these asymmetries are zero. And it's not difficult to calculate this asymmetry from the standard formula, which I already discussed many times. And here's the result. Delta Cp E mu is equal to delta Cp mu tau equal to delta Cp tau E, and I denote this by delta P. And similarly, instead of Cp, I can put the superscript T, as I already discussed. And the expression for this Cp and T violating probability difference is given by this formula. It's a very interesting formula, actually. Let us look at it. It contains sines and cosines of all mixing angles. It contains sine of the Cp violating phase delta, and it contains the sum of sines of three oscillatory factors, those three oscillation phases. Now, first thing to notice that unlike the standard two-flavor probability, we have signs here and not sign squared. Okay? What does it mean? This means that if we have a situation where the phases are very, very big and we have to average them, the mean value of sign for big argument is 0. The mean value of sign squared is 1/2. But mean value of sign is 0. So if the oscillation phase is very big, it all averages to 0. What happens if the oscillation phase is very small? The same. We can expand sign in terms of its argument. The linear terms exactly cancel. The 3 linear terms cancel each other exactly. Just because there are only 2 independent mass square differences out of 3. So if you calculate this, only cubic term in L survives. For small distances, this is again a strongly suppressed quantity. Moreover, it is 0 if any delta m square is 0, it's obvious. For example, if delta m square 1, 2 is 0, delta m square 2, 3 is equal to delta s minus delta m square 3, 1. And these 2 terms cancel each other. This quantity vanishes if any of the mixing angles is either 0 or 90 degrees. So there are many limits in which this vanishes. And this explains why it is so difficult, in fact, to measure it experimentally. It's one of the reasons that this is actually a small quantity. We expect it to be a small quantity. By the way, this factor here, by analogy with the quark physics, is sometimes called the Yarskov invariant. For those who are familiar with Yarskov invariant in the problems of CPU evaluation in hadronic physics, this is the leptonic analog of the Yarskov invariant. It is invariant with respect to the reparametrization of the leptonic mixing matrix. Okay, now, as I mentioned already, the mass square difference which is responsible for the solar neutrino oscillation is about a factor of 30 smaller than the other one. So we have one small parameter in the neutrino oscillation theory, in the 3-flavor neutrino oscillation theory. And in addition, as we know now, actually we knew that a long time ago that the parameter u is 3 small. Now we know that it's non-zero. It's actually not too small. It's about 0.16, as we recently learned. But still it's a relatively small number. So we have 2 small parameters in the theory of 3-flavor neutrino oscillations. And this allows us, in the first approximation, in some cases, reduce the full 3-flavor problem to a much simpler 2-flavor problem. Consider neutrino oscillations as 2-flavor problems, as a sequence of 3-flavor problems. However, this is not always possible. And in addition, if we really want to have very accurate expression of the oscillation probability, you have to take into account all 3-flavor effects. And now we are in a situation in which we are interested in very precise data. Neutrino physics entered the era of precise measurements. We have now very, very precise results for the neutrino parameters. And in most cases, we cannot ignore 3-flavor nature of neutrino oscillations. Okay, now I'm going to switch to a completely different topic. So if you have any questions, please ask.
One question. On the previous slide, there was something special about cosine and theta 1.
Sorry, once again?
On the previous slide,
Yeah.
with this Yarskov formula.
Yeah, you mean this is entropy squared. This is just because of the standard parameterization, nothing special. None of this mixing angle is special, but one of them always enters a square. In this particular case, it's theta 1, 3, just because of the parameterization we have chosen. If you choose a different parameterization, different angle will enter in this way. More questions?
Is any of nowadays or future experiment sensitive to delta M23?
Delta M 23?
Yeah.
Yes. All the atmospheric neutrino experiments, which are still ongoing, like super command counter, for example, and long baseline accelerator experiment, they're all sensitive to theta 23. Moreover, actually they call it theta 3.1 because 3.1 and 3.2 are nearly the same because the difference between them is very small. Moreover, recent experiments which measured the last mixing angle, theta 1.3, are also sensitive to this. The Reno, diabane, and double show experiments, which also T2K accelerated experiment, and the first three which I mentioned are reactor experiment, they are all sensitive to this large muscular difference.
Is there something like voltage parameterization in
people tried this, but it didn't turn out to be very, very useful in this case. Well, you see, the reason is that there are essentially no small parameters. Unlike in the quark center, the mixing is pretty big, which was a big, big surprise for many people. People expected that leptons are probably similar to quarks, and the mixing should be small. It turned out that it is not. By the way, it's kind of a little philosophical statement, but in my mind, this may be a hint that neutrinos are Majorana particles. Because if we introduce the neutrino masses exactly like the masses of charged leptons and quarks, then we could in principle expect small mixing, because what does this small mixing in the quark sector mean? This means that the structure of the mathematics of up-type quarks and down-type quarks are similar. Even though the scales are different, but the structure is similar. This means that the unitary matrices which diagonalize them also have a similar structure. And therefore, U dagger times U, one for up-type, another for the down-type quarks, nearly gives one unity. So one, in principle, could expect the same situation if neutrinos were Dirac particles, if all the masses would come from Yukawa couplings as in the standard model. And it's not a proof, but it's kind of hint that the fact that the neutrino mixing parameters are completely different, quite big, may be due to the Majorana nature of neutrinos, which is not possible for quarks as we know. And that may be behind the large mixing angles in the neutrinos in electronic sector. There are many arguments why neutrinos are probably Majorana. There is no proof, but there are some good arguments why neutrinos should be Majorana particles. This is one of them. Okay, if there are no more questions, let me move to a different topic. This is neutrino oscillations in matter. I'm going to discuss the MSW effect. This is actually the resonance enhancement of neutrino oscillations, which is possible if neutrinos propagate in matter. This was discovered by Mikheyev and Smirnov in '85, and they based their work on the previous paper by Wolfenstein, which laid the basis for this kind of description. And it turned out that meta can change the picture of neutrino oscillations in a very significant way. In principle, it turns out that even if the mixing angle was small for neutrinos, and we know that at least one mixing angle is small, the oscillation can be strongly enhanced in matter. Typically, if the mixing angle is small, you remember the mixing angle gives us the amplitude of neutrino oscillations. So if the mixing angle is small, you expect the oscillation factor to be small. In meta, this may not be the case. Meta can strongly enhance mixing even if it is small. And that was a big surprise to many people, and it was a very beautiful finding which was exciting to many people working in the field. It turns out that the MSW effect, the resonant enhancement of neutrino oscillations in matter, is actually responsible for the conversion of solar neutrinos. I mentioned before that the solar neutrino experiments observed some deficiency of the signal from solar neutrinos compared to the expectation. This was dubbed the solar neutrino problem. And the solution of this solar neutrino problem turned out to be the so-called large mixing angle MSW effect. And it was established in a series of very beautiful experiments. It was not immediate that people found out that this is the solution. There are other competitors to this solution, other suggestions. And it turned out that the true one is the resonant neutrino oscillations in matter. And you can see the authors of this effect: Lincoln, Wolfenstein, Stas Mikheyev, and Alexei Smirnov. Unfortunately, Stas Mikheyev passed away 2 years ago. Okay, now I mentioned at my first lecture that neutrinos interact so weakly with matter that the mean free path of 1 MeV neutrino in lead is 1 light year. In lead, which is a very dense material, a heavy material. So how come the matter of the sun or of the earth, which is much less dense, can affect neutrino oscillations? The answer is the following. When we calculate the mean free path, it's given by this formula where the cross-section of neutrino interaction of matter is proportional to the square of the Fermi constant, which characterizes the weak interactions at low energies. And we know that it's a very small quantity. In the case of neutrino oscillations in matter, what is important is neutrino forward scattering on the particles of the matter. And the forward scattering is coherent. And in this case, the amplitude of this process is not proportional to Fermi constant squared, but to Fermi constant. The potential which is produced by matter for neutrinos is linear of the first order in Fermi constant. That's one explanation of why the matter may be important for neutrino oscillation. Another explanation is that we have to compare the potential produced by matter for neutrinos, which turned out to be Fermi constant times the number density of the scatterers of the matter. We should compare it with another small quantity, which is delta m squared divided by twice the energy. You remember this quantity always enters on the unit of neutrino oscillation. Neutrino energy always comes through delta m squared over twice the energy. And this is also a very small quantity. And if it turns out that two small quantities are of the same order, then of course we can expect that neutrino oscillations can be modified. Now I mentioned coherent forward scattering. Why the forward scattering is coherent, and what do I mean by this? Coherence means that we should add the effects of different scatterers on which neutrino can scatter at the amplitude level. So we should add the effects of the amplitudes of scattering and not the probabilities. Why it is important that it is a forward scattering? Because if the scattering is not a forward one, if the momentum of neutrino is changed, this means that part of its momentum was transferred to a particle on which it's scattered. But if it is transferred to a particle on which it's scattered, we can detect this recoil, and we will know on which exactly particle neutrino is scattered. And if we know that exactly on which particle neutrino is scattered, the coherence is lost. We cannot take some coherently the scattering on different particles. That's very simple quantum mechanics. So the forward scattering is coherent. Okay, what actually happens when neutrinos propagate in matter? They can, well, let's consider normal matter. By normal matter, I mean matter which consists of nuclei, protons, neutrons, electrons, and no other particles. Okay? In this case, neutrinos can interact with electrons through the charge current interactions, W boson exchange, and with all particles through the Z boson exchange. And in the first interaction, only electron neutrinos can participate. This is simply because there are no muons or charged ions in matter, in normal matter. By the way, the situation in supernova can be quite different, but I'm not talking about supernova. So these are the interactions which can give rise to the potential for neutrino in matter. An important point is that the neutral current interaction is flavor blind. Flavor blind means that the Z boson doesn't care which neutrino is scattering through exchange of this Z boson. So these effective potentials induced by this diagram for neutrinos of all three flavors, electron, muon, and tau, are exactly the same. But we know that the same potentials would modify the phases of all three neutrino flavor states in the same way. And we know that only phase differences matter, not the absolute values of the phases, only phase difference. Because of this, we can ignore completely the neutral current contribution to the neutrino potential. It is there, but it doesn't affect neutrino oscillations. So we can forget about it. And only consider the charge current contribution. And this charge current contribution turns out to be simply given by square root 2 times Fermi constant times the number density of electrons in matter. And in my previous lecture, I think I discussed the evolution equation for two-flavor neutrinos in vacuum, and it was given by this expression except for this term. Okay? Now in matter, only electron neutrinos experience this charge current interaction, so we should add this potential only to the electron type, electron part of the effective Hamiltonian describing the evolution neutrinos in matter.
Is it obvious?
Sorry?
Is it obvious?
Yeah, but because look here. So this is the flavor plate base, E mu. So if there was a transition from electron neutrino to muon neutrino, then there will be some non-diagonal term. Okay? There is no such transition. Or if there was such contribution also for muon neutrino, there will be also a term here. But there is no such contribution because there are no muons in normal matter. Electrons are there, they have atoms, but the muons are absent. So there are no contribution here. And therefore there is only contribution in this place, which is the potential created by matter for electron neutrinos. I hope this is clear. If it is not clear, please ask again. That's very important. Actually, this is the most important equation for neutrino oscillations in matter. And all the rest will be derived from this equation.
Could you please tell again how we thrown out the neutral current?
Sorry, once again.
What about neutral current? What happened with the neutral current?
The neutral current. As I said, it is present. Of course. So what if we calculate this contribution? We have to add the same terms here and here. But if we add the same terms here and here, you remember we can always subtract a matrix which is proportional to the unit matrix from the Hamiltonian. It was one of the problems I asked you to solve, to demonstrate that this does modify the oscillation probabilities. So we just subtract these terms which are the same on the diagram. And we get rid of the neutral current contribution. It is there, but it doesn't affect neutrino oscillations. It is important if there are stereo neutrinos, which I'm not discussing now. But let's postpone this one. Okay, now how do we calculate this potential? I said that it's given by this expression, but can we calculate it? Let me try to explain how it can be done. We consider neutrino interaction with electrons at low energies, so we can just consider the effective 4 fermion Hamiltonian, the standard one, Hamiltonian of neutrino electron scattering, G Fermi over square root 2, and two currents, electron neutrino and neutrino into electron transitions, charge currents. Then we can use the so-called Fierce transformation to move one of the electron fields here and respectively the electron neutrino field here and the electron field on its place. It's a simple algebraic transformation. You can find the proof of this, for example, in the textbook of Itzikson and Zimmer on quantum field theory, and many other textbooks. That's a pretty standard thing, just a simple algebraic transformation. And if you do this, you end up with this expression, which is much more convenient for calculating the potential created by electrons for neutrinos in matter. Next, what we want to do is the following. We follow the property of a given neutrino, but we integrate over properties of all the electrons in the medium. Okay? So we fix the variables which correspond to the neutrino, and we take the expectation value over the state of the electrons in the medium. This is not the vacuum expectation value, actually. This is the expectation value over the macroscopic state of matter. I average over all the electron variables. Okay? So these expectation values should be understood in this way. Expectation value over the state of the matter. And here we have different contributions coming from vector current, axial current, for electron, time component, and spatial component of this current. Okay? Now, if we take the part which contains E bar gamma 0 E, this is just the same as E dagger E, and this gives us the density of states of electron. When we average it over the state of the matter, it's just the number density of electron, nothing else. If we take the expression which contains E bar gamma vector E, it gives us the average velocity of electrons in the medium. This was coming from the vector kind. If we take axial vector kind, then there are expressions which are the average projection of the electron spin on the electron momentum and just the average polarization, the spin of the electrons. Now, if we consider a matter in which there are no fluxes, so the average velocity of electrons is 0, and the matter is unpolarized, so the average spin is 0, then only one term contributes. This term, which is proportional, is equal to the number density of electrons. It's actually number of electrons per cubic centimeter, nothing else. And then we get extra factor of 2 here, because when we add by 1 minus gamma 5 on the left-handed neutrino, we just get twice this left-handed neutrino field. And this gives us extra factor of 2. Therefore, instead of G Fermi divided by square root 2, we get G Fermi multiplied by square root 2. And then it's multiplied by the electron number density. That's the way, the simplest way how to obtain this potential for neutrinos in matter. And for now, we don't need anything else. They have the evolution equation, and we know all the terms in this, all the parameters in this evolution equation. Next, let us go back to this equation and assume that neutrinos propagate in a matter of constant density. This need not be the case. For example, in the sun, the density is not constant at all. It's very high in the center of the sun and nearly 0 on the surface of the sun. Also in the Earth, the density is not constant. But just for simplicity, to start with, consider the case in which matter density is constant. In this case, we again have a system of 2 coupled equations with constant coefficients, and it's very easy to solve it. But we don't actually have to do it again because we already know the solution. We have exactly the same situation for neutrino oscillations in vacuum. So we should obtain a formula which resembles the probability of neutrino oscillation in vacuum, except that the mixing angle will be different from the vacuum mixing angle, and the oscillation length will be different from the vacuum oscillation length. And we know how to calculate these parameters. Remember, I told you that to calculate the tangent of twice the mixing angle, we should take the off-diagonal element and divide it by the difference of the diagonal elements. Okay? And the important point here is the following. In the absence of this potential, the difference of these diagonal elements cannot vanish. It's always non-zero. However, if we have an extra term, the potential term present here, there may be situations in which the difference of these diagonal terms becomes 0, which means that the mixing will be strongly enhanced. And this is exactly the Amsdale effect. Now let me go to the next formula. So the transition probability for neutrino oscillations in matter has exactly the same form as the oscillation probability in vacuum, with the sine square of twice the mixing angle in matter, which is different from the vacuum mixing angle, and the oscillation length is matter, which is different from the standard oscillation length in vacuum. Now, the amplitude of oscillation is again given by sine square of twice the mixing angle in matter. And by doing the manipulation which I just described to you, first calculating the tangent of this mixing angle and then finding this sine square of this twice mixing angle, we find this expression. This is the amplitude of neutrino oscillations in matter of constant density. And you immediately see that it has a resonance form. If this term here vanishes, then the sine square of the twice mixing angle in matter becomes unity, because the numerator and denominator will be exactly the same in this case. And if this term vanishes, so we have 1 for sine square of neutrino oscillation angle in matter, twice neutrino oscillation in angle, mixing angle in matter. And this means that we have a strong enhancement of neutrino oscillations. What is interesting, that this happens irrespective of how small the mixing angle in vacuum is. Irrespective of this will be 1 at the resonance. however small the mixing angle in vacuum, the mixing angle in matter at resonance will be such that sine square of this mixing angle is 1, which means that the mixing angle itself is 45 degrees. The oscillation length in this case is given by this expression. It can be expressed through the oscillation length in vacuum times this parameter. And this is actually the plot for sine squared twice mixing angle in matter as a function of the density. At zero density, it coincides with the mixing angle, sine square of mixing angle in vacuum, which I consider to be small here. Then, with increasing density, it also increases, and it reaches 1 at the MSW resonance. And then, with further increasing density, it decreases, and then it goes to 0. So, at very high densities, the oscillations are suppressed again. So, there is an optimal density at which the oscillations are enhanced, and at too small densities, it's just a mixing angle in vacuum, and at very high densities, the oscillations are suppressed. Now, the oscillation length in vacuum is given by this expression. And now I can ask the following question. As I said, the amplitude of neutrino oscillations in matter becomes equal to 1, no matter how small the mixing angle is, if they are at the resonance. Doesn't mean that we can just consider the case where the mixing is absent at all, and we still have some oscillations in matter. As I said, here, at the resonance, this is always 1, independently of value of the vacuum mixing angle. What happens if the mixing angle in vacuum is exactly 0? Should we still have oscillations in matter? Well, the answer is formally yes, but in reality, no. Look at this. The oscillation length becomes infinite in this case. The mixing angle becomes 45 degrees formally, but the oscillation length becomes infinite. So we cannot see any oscillations at all. Okay, I think I will stop at this point. So if you have questions, please ask.
Was that experiment on the brewer?
Yes. I will discuss in the next lecture the experimental confirmation of this effect. Well, I should say there's a very strong evidence for this effect, but there was no direct proof. Direct proof would be, for example, the day-night effect in the solar neutrino experiments. This was not found because it is predicted to be relatively small. The present day experiments are not sensitive enough to it. However, if you just try to describe all the data without taking matter effects into account, you get a very bad fit. And if you take it into account, you get an excellent fit. That's an answer. So in this sense, it was established. Also, the spectrum of solar neutrinos was measured by combining results of different experiments. Different experiments are sensitive to different parts of the spectrum of solar neutrinos. And the Akhmedov effect predicts a very particular distortion of the spectrum of the solar neutrinos. And this distortion was experimentally confirmed. In this sense, it was confirmed.
Okay, more questions? I'm sorry, maybe I'm too stupid, but is the only way to enter the potential? Because the first things that came in my head is that I should write something like kinetic equation when I have any relation with that. But why do you write the Schrödinger equation?
You mean this equation?
Yes. Is it the single way, or absolutely, or not?
Well, different things. First of all, if you want to study the neutrino properties in, for example, in supernovae or in the early universe, you really need some kind of kinetic equations to study kinetic equations. Because it's a complicated dynamical system with high temperature, high density, and so on. In normal situation, it's enough to study, so you can neglect, for example, the back reaction of neutrinos on the medium. You can consider medium as to be frozen. So the properties of the medium do not depend on what happens with neutrinos. Okay? So if you assume this, It's just enough to consider the potential which is created by medium for neutrinos. That's the answer to the first part of the equation. The second part, why it is a Schrödinger equation? Well, this is kind of heuristic argument, which I started in the previous lecture when I derived this equation for neutrino evolution in vacuum, and then I modified it in matter by adding the potential. And I demonstrated that you get exactly the same result. So some people ask why it should be Schrödinger equation, nothing else. Schrödinger equation many people consider as a non-relativistic quantum mechanics. Okay, that's not true. In quantum field theory, the evolution of the neutrino or the state of your system is also given by Schrödinger equation. That's quite general. It's not necessarily non-relativistic quantum mechanics. And especially here, it's not the evolution, for example, in some spin space or whatever. It's evolution in the flavor space. So the fact that neutrinos are relativistic doesn't prevent us from using the Schrödinger equation. In order to be more rigorous, you have to consider a quantum field theory approach. Things will be much more complicated in this case, but the result will be the same. So what you have to do is the following. You have to calculate the full relativistic propagator of neutrino and find out which equation it satisfies. Neutrino in matter. So that's not a simple thing. The propagator of relativistic neutrino in vacuum is very simple. Like
do you mean something like Bethe-Salpeter equation? Or
sorry?
Do you mean something like Bethe-Salpeter equation?
It's the Schwinger-Dyson equation. You calculate the propagator of neutrino in matter of non-constant density. That's not trivial at all. For matter of constant density, it's easy. But for matter of non-constant density, not trivial. But then you can show that the result will be the same as simply using this Schrödinger equation.
Thank you. Okay, if no more questions, please thank the speaker.
Nie, to już tam dość.